This is section 642, right? Siri.
Yes, sir.
Okay, Siri Poop is here. Okay, only me and you. Just wait for your friends to come.
Ajahn, so our report we submit in AULNS line.
Right,
Okay.
right. Yeah, there is an option there. So if you go to AULMS and yeah, this one, Digital Logic Design Lab, here, you're supposed to submit here, okay? Yeah, I think everybody submitted already, 23 out of 25 students. Okay. All right, good afternoon to you all. Let's start by checking the attendance. And then we start the 2 days. This is the second time we meet, right? We start the 2 days experience. All right, so annotate PDF. 640. Okay. Oh, we have only 9 students. Okay. Here. Adib is not here. Nata Chanon is here. What happened to you last week? Were you here, Nata Chanon?
I'm here, sir. Yes.
No, last week.
Oh,
you
yeah.
Absent, right?
I wasn't there, but I have sent you the.
It's okay. Yeah, the session is recorded already, so you can always go back and watch it.
Yes, sir. Thank you.
Okay. Sheshang. Okay. L dot.
Yes.
Here. Okay. Bonsu. No. Rabbit. Cable. No. Yapeng.
Yes.
Yeah. I think you send me your report in chat room in Microsoft, right? Upload in LMS, okay, Yapeng?
Okay.
Siri Boop. And LDA. All right, okay. So in previous semesters, I set the due time to 9 a.m. And then I had a lot of difficulties because usually you guys, you tend to do your homework maybe one night before the class, and then usually you cannot finish it. So in previous semesters, I noticed that a lot of the students, they fail to submit and they come to the class and I say, oh, John, can you open the option, please? And they send me an email and bother me a lot and annoy me a lot. So now I learned that instead of 9 a.m. or even 1:30, I set the time to 4:30 p.m. So you actually still have time, okay? So you see, the due date is on Friday till 4:30 p.m. You see that? So it's going to be like this every week. And I think it's enough time for you to submit, okay? If you fail, you will still actually have the chance. You can submit later on, but I'll cut mark, okay? I consider that as a late submission and then I cut mark. Yeah, actually before I was very strict, so after the due date and time is passed, I would never ever let any student submit. But you guys, your performance is so low, it's just so bizarre. Anyway, but I decided to cope with you. That's actually one of the elements of being clever, right? So if you look at even in the animal kingdom, those who have high IQ or higher IQ, then they kind of more willing to adapt to their surrounding and changes and You know, when things change, they try to adapt. Okay. And if you find yourself very difficult to adapt to the new situations, then you kind of like should adopt about your IQ, really. If you are clever, you always have to adopt. But if you don't, then you're going to be eliminated. You're going to be wiped out. That's actually the law of nature. Only the people or creatures that are willing to adopt shall survive. Okay. Yeah. Anyway, so now I'm adopting to you. It's actually sad, but it brings me more happiness, because otherwise I have to keep, you know, reading emails and replying and open the option again and again and again. So there is no actually cut off date. Okay, so this always will be open, and if you submit, then I might give you some mark, but then I consider it as a late. Anyway, so we did the attendance already. Now let's go to Control N. Okay. Let's check. You remember the last assignment I asked you to go and find out 3 simulators, right? Now, what I'm going to do is that I call your name, and then in the chat room, you just mention this. Oh, audit is here. Okay. How about Konsu? Not yet. How about Korabit? No. Anyway, you mention the 3 or whatever number of simulators that you tried by yourself. Okay. So you right now you should do something like this. You just open your notepad. Okay. And then you just mention the name of the simulators that you try. For example, ABC simulator, number 2 is Sim, whatever. Okay, number 3 is XYZ simulator. And prepare this, and when I call your name, you just copy this and paste into the chat room, so I can know the name of the simulators that you try. Then at the end, we will run this statistical kind of like consensus to see the most popular simulator in this chat room, okay? In this class, in this session. So let's go here, and who is the first one? Audit. Audit, tell me what simulators you try. After that, Natachanam. And then Sheshe Hang. Tell me the name of other students, also prepare the list. Tell me what you have tried so far.
Ajahn, Logic Friday did.
No, type in the chat room. Type in the chat room, as I told you. Come on.
Can I send first?
What's that? Nobody? Come on, tell me your. Oh, okay. So Natachanon, we have 3 simulators. Okay. This is Natachanon. Circuitwares, logically or logical-y. Every circuit. Okay. This is Natachanon. Okay. How about audit? How about Sheshehang? How about L. Kayeng? Okay, L. Circuitwares. Okay, so we have 1 vote for circuitwares. And then Okay, another voting for here. Then part SAM. Okay, part SAM or part, this is new one, or part SIM, whatever. So audit logic Friday. Wow. Deeds CEDAR logic simulator. Is this audit? Is this one simulator or four? The comma means four? Four simulators?
No, Ajahn, 3.
Three. Logic Friday. Okay. And what is Deeds? The name of simulator?
Yes.
Okay, Deeds is another one. And okay, wow. You use, I never heard of this. Very unconventional ones, okay. And then Siri Pope. Logically, so 1 plus 4 here. And circuit verse, okay. Then Dominic Force, wow, this is a new one too, wow. Okay. Sheshahang, every circuit. Wow, what is this one? QUSC, okay. And multimedia logic, okay. Okay, wow, a lot of simulators. Now, how about this Konsu here?
Ajahn?
Yes, hold on.
Mine, the last one is Patsim. I wrote wrong. Instead of Sam. Instead of Sim, I wrote Sam.
Yeah, it's okay. L dot, I can see. Circuit verse, okay. Logically, okay. And circuit lamp, okay, circuit lamp. Wow. Okay, anyone else? L dot, you told me Siri Pop, you told me already, okay. Yapping, how about yapping? Yapping, you didn't tell me. Oh, yapping here, okay. Logic simulator. Oh, this is new. What is this one? Logic simulator, okay. Oh, logic Friday, logic simulator. And logically again, okay. And part sim. Is part SAM, do you mean part sim or part SAM?
Yeah, it's Patsim. I wrote wrong. I already modified.
Ah, okay, so part sim is, okay. Okay, so 1 vote for part sim. Okay. Yapeng. How about this Konsu? Konsu is not here, no. Rabbit, no. So these two are absent. Okay, whatever. All right, now you have a kind of picture, better picture, okay? So as you see, this is the most popular one, logically, all right? So let's go and see what is it. The one that 5 students use this one, 5. Okay, so, oh, so this is not actually free. Yeah, you have to pay around $60 per student, or a classroom $600, or a campus $1,200. Oh, okay. So now, can you tell me? Try online. If I use logically, can I have a waveform? So I'm going to explain to you what is a waveform. For example, if I set up an AND gate waveform, okay, then I'm supposed to see something like this. If the simulator supports the waveform, yes, you see, something like this. This is called a waveform. It shows you the value of the output on every instance of time, okay, when the input changes. For example, 0, 0 give you 0. The only time, oh, this is not actually and, right? I think this is or. This is or, okay? So this is OR gate. If one of the inputs are high, then the output is high. Can you see that? When both the inputs are 0, then the output is 0. So this is called the waveform. Now, those who use this one, can you tell me if I can use the waveform or not? For example, I place AND gates. Okay. Is there a waveform here? Can I generate a waveform? So I connect this, Okay, light bulb maybe. Bing. So this is AND. Okay, this one works. Can you see? It works. But is there a waveform? Those of you who work with this, I think no. There is no waveform. So I cannot generate something like this. I cannot generate, okay? So that's the problem. So even this is the most popular one, but this one doesn't have a waveform generator or something like a logic analyzer or oscilloscope. So I can see the change of the output across a time period. I cannot see that, right? I can just, you know, see the simulation running instantaneously, and then I can change the input and the output changes. Okay, now why is it important? Because today's experiment needs you to grab the waveform of your circuit. So actually you cannot use this one. Okay, so those of you who pick this one, you just can't use it because it doesn't, for the today's experience, right? You can set up the circuit using this one, but then how you gonna show me the result in your report? You cannot, because this one does not support waveform generation. Okay, now what is the next one? The next one is circuit verse. Okay, so this one, launch simulator, is it free or not? For teacher, for contributor, launch simulator. Okay, this seems a little bit more advanced maybe. Now those of you, 4 students here, use the circuit verse. Can you tell me if I have the option of generating tools, combinational analysis? It's more advanced, okay? You see, it can export Verilog. Later on, you will know what is a Verilog, okay? It's programming language. Describe the hardware, but no, you can. So you cannot use this one too because it doesn't generate. Yeah, it doesn't generate a waveform, okay? Now, this one does, okay? But unfortunately, this one is not free. But for now, the morning session, they told me that for small circuits, actually, you can set up and it's free, okay? So you actually can use this one. I suggest you use this one, okay? Yeah, I click on Firefox. This one is okay, not bad. Yes, you see, wow. This one has, can you see? I'm looking for this. Can you see this one? This is called the waveform. It's like a oscilloscope. It shows you the waveform, okay? Now, those of you who use this every circuit, can you tell me how to set up the digital AND gate, for example? I think, okay, this is very complex, actually. You have to learn this. You have to learn this. It's not easy, right?
Sir, I actually use every circuit for your week 0 report. And I just found out that it is not a perfect square. Like, it's not a perfect square waveform, just like that.
Okay. So where is the logic gate?
On the right, you have to scroll to the.
On the right, right? Where? New, I click
No,
new
you
circuit.
have to scroll. You have to scroll horizontally.
Can you show me? Can you show? Do you have the circuit? Can you share
Yes.
your screen?
Okay.
Share
Okay.
your screen. Share your screen.
Okay. Wait 1 sec, sir. I have to add the device.
Okay. So what I'm looking for, okay, is I think this one can generate a waveform. Okay, your friend going to show you. But we have a lot. Now look, in the morning session, okay, that's the result we got. Similarly, we got the logically as the most popular one, and circuit verse was the second one. And actually, every circuit, you see, is the third one. So this one can generate the waveform. There is another option that you can use, MATLAB Simulink, okay? I'll talk about this too. This one, as you are, as the student of Assumption University, you can actually have the MATLAB version, MATLAB student version, or maybe even the full version for free, okay? Because you have the academic email. Then, so you have to either download this one, okay, MATLAB and Simulink, or download the full version using the Assumption University account, okay? So I'm gonna explain what is this MATLAB later on. But using this one, MATLAB, Simulink, Digital, Logic. Oh, wait. MATLAB, yeah. Yeah, you see, implement logic gates in MATLAB. You have to follow this tutorial, okay? Just watch it when you're at home, okay? Now, this one also can generate a waveform, okay? Yeah, you see? So logic gates and this is AND gate. Display. Here you can, I'm sure 100% you can generate the waveform, okay? MATLAB is professional.
Sorry,
I don't think I
sharing
can
the
see it.
screen.
Yeah, share your screen. Now your friend gonna share the.
Oh, okay. Can I share it now, sir?
Yes.
Yeah, okay. Yeah, so it's basically something like this.
Okay, wow.
This is a logic source, and if I change it.
Wow, this is nice. Wow. Yeah, this is good.
It's not a perfect square waveform.
Yeah. Yeah, this is correct. That's what I want. So you have to actually capture the output, and then you have to capture the input too. So you have to have at least, for example, 3 or 4 channels, okay? Now the reason that, yeah, this is nice. Where is the logic gate section? Oh, I can see up there. Can you show? What gates do they have?
Scroll it like
Oh, here. Okay. Yeah, they have everything. They have. I see. I can see now. They have the AND, OR, inverter, NAND, NOR, XOR. Yeah. So can you prop two points or not? Like, can I see the input and output at the same time?
Oh yes. So you have to press this.
Okay, and then change the input and see what happens. But the input and output are the same, I think.
It's 2 input NAND gate.
No, this is supposed to be 2 input. Yeah, this is correct. Okay, yeah. But milliamp, why we don't want milliamp? We want the voltage. Look at the green one. Green one is right. And why is it up to 10? 10 volts? Oh, because of 1 volt. Supposed to be, yeah, I don't know what you're doing here, but yeah, something like this, okay? So for your next week, when you want to submit your report, right, I want a waveform like this. So if the input, for example, your circuit has 3 input, then you have to show me, yeah, this is correct. Now the yellow, what is the yellow one? I don't know. But yellow is milli. So you have to actually, yeah, I don't know what's the yellow one. You have to tell me.
So basically, you can display the waveform any
Yeah.
way you want.
What you
Like,
should
for
do,
example,
prop the input. The green one is the input, okay?
yeah, the
And
green
then
one is
prop the point before the diode, not that one. Before that diode. Yeah, here. The output.
I'll have to
Yeah,
move.
prop.
I'll have to move this.
Yeah, why you have the voltage there? I don't understand. Why you need that?
If you want to measure the voltage, you
Oh,
have,
that's the voltmeter. Oh,
yeah.
okay. Your mistake is this. The plus is correct, but the other side you connected to ground.
Oh.
No, your voltmeter. Your voltmeter, the other side you connected to ground after the diode.
Oh.
Yeah, go there. Yes, over there. Correct. Now measure. Okay.
Yes.
Now change input. This is not correct. Yeah, this is correct. You see, this is correct. Now, can you add another voltmeter and put it in the between of the two NAND gates? Another one.
Okay.
Second one. Another one. One side to the ground. No. One side to the ground. The ground. To the ground. Another side to the second input of the second and NAND gate. Yeah, this one. Yeah, correct. Run.
Okay, I'll have to put on display.
Okay, this is correct. Okay, run. Change something. Yeah, this, you see, this is correct. Actually, the other one is the inverter. Can you see? But now the signals are overlapping. Now you have to find a way. This is correct. Okay, to do something to separate the signals into different channels. There is a way probably, but I don't know how. Okay, yeah, maybe that one. So you should show all of them not overlap like this, but on top of each other, like 3 channels. There must be a way. There must be.
I don't know how to.
Yeah, you have to play with this. Okay, so
yeah.
It's okay. Now I'm gonna show. Let me share. I'm gonna show you what I want. Okay, so you should be able to get something like this. You see, these waveforms, right? They are not overlapped. Can you see? They are separated on different rows. Okay, that's what I want. And your simulator should be able to give you something like this. Okay, there are some settings that you have to play with. Now, let's go to, what is gate sim? I never saw the gate sim. What is this gate sim? One student use gate sim. Seems interesting. What is it? Gate sim. Wow. Gate sim. Oh, okay. This one, this one has it. You see, that's what I want. Can you see? That's what I want. A, B, C. In your report, you should give gate sim has it. Gate sim. Okay. You see? So that's what I want. You should capture this and give me this gate sim. Is it free? Yes, it's free. You can donate. Very nice. So you download. So this one is a good one, and it has the waveform generator. Can you see? Use this one. Okay. Very nice. Gate sim. Okay. Logic sim. Every circuit is okay to logic sim. This is okay. Seems okay, but I'm not sure if it can generate logisim waveform. Yes, this one can. Okay, so you can use the logisim too. You see, that's what I want. So you set up. This is the logisim. Okay, you set up, and here you see. Now at this point, this guy actually, what is this? Chronogram. They call it chronogram. Okay, sometimes, yeah, you see, they're generating the, yeah, you see, that's what I want. That's what I want. So here you actually can see the signals going up and down. They are not overlap like what your friends show, okay? They separated into different channels, okay? We call this logic analyzer, okay? But sometimes in different programs, they have different names. For example, here they call it chronogram, okay? Yeah, so try, okay? What you have to do, I just show you, let me go here. A lot of, what is this fault system? Oh, this is for morning session. Yeah, so there are a lot. You see Dominic force. Let me see this one. Interesting. Dominic force. Dominic force. Logic. Logic gate simulator. Dominic. Which one is it? I cannot find it. Dominic, we don't have Dominic force. Add we don't have that. What is this? SEDAR logic simulator. This is also, I never heard of this one. SEDAR. Oh, this is nice. Yeah, it's true. So how does it look like? Okay, so this looks like this. I think this cannot maybe generate waveform here. Adi, I'm not sure. It doesn't look very professional, but you got my point, right? So we have a lot of simulators. One good one, the morning student. This is actually LTS Spice. It's very famous. This is the most powerful simulator when you want to simulate analog signals. This one, LTS Spice, and it's free. Okay. We have a series of, we call them a SPICE-based simulator, a SPICE, okay? So a SPICE simulator, you can have simulation software, okay? This SPICE is not free. Oh, this one is open source. One of them, PS Spice, I think PS Spice, okay, PS Spice. One of them is not free. Yeah, this one is not free. It comes from the ORCAD, okay? So you have to pay PS Spice to simulate every kind of circuit that you want, okay? How to buy resources. Anyway, but the academic version, they call it LT Spice, LT. There are many actually, you can, and LT Spice waveform, you see? Waveform viewer. So it actually can give you, that's what I'm talking about, can give you the drawing like this that actually shows how the signal changes across time. Okay, you see this one. So you can use this one too, but this is actually not user friendly. I think that one that I showed you was the Logisim. Okay, but it's completely up to you. You can actually try many. Okay, up to you. You can learn to. But in week number 4, I will tell you what simulator to use. Not now. Now it's freestyle. You can do whatever you want. So SPICE variants. Let's see if I can find a SPICE simulator. Yeah, this one. Yeah, you see, this one also have a lot of commercial versions. For example, iSpice, PSpice, PSpice. And then you have the free versions like LTSpice. And what others? Spice 2. Read this, okay? Spice is actually very, when I was a student, I use the Spice. Up to my PhD program, I use the Spice. This is very powerful and free. It's free and it's very actually advanced. You can control all aspects of the simulation. Yeah, you should know what are these things. Anyway, it's very actually difficult. The learning curve is steep. All right, now there is the other one that I want to talk is the MATLAB sim. You actually can use MATLAB. Okay, is there anybody here who knows what is MATLAB? MATLAB.
I know.
Siripov?
Yes.
What is it?
MATLAB is some computer program language used to calculate something difficult, for example, calculate metric like that.
Matrix, yeah, correct. Yeah, I'm gonna give you an in-class point. Yeah, so you see, your friend mentioned, he said, first of all, it's a programming language, okay? And then he meant, this is actually a very famous task usually done in MATLAB very easily, which is matrix arithmetic, okay? So DLD lab, in class points. Oh, I have it here. So this is section 642. Section 642. So this in-class points will actually help you at the end of the semester. When for example, if you get A minus, I will change it to A. Okay. What was the name of the student who? Oh, Siripon, right?
Yes,
Answer. Siripon. Okay. Yeah. Your friend is right. Siri PHOP. PHO.
PHOP.
EB. Okay. All right. Don't worry. Don't worry. Okay. So your friend is right. MATLAB is a programming language, okay? But let me explain because this is important, okay? So programming language means you program a computer, right? You give an algorithm to a computer, a set of instructions, and the computer runs it for you, okay? So this is your computer. Now, every computer has a very important component, we call it processor, okay? This processor, or CPU processor, or central processing unit, okay? CPU has what we call the instructions, okay? And then the set of all these instructions, we call it an ISA, instruction set architecture, okay? For example, your iPhone, okay? Let's go iPhone processor, okay? The processor, the brain, the component inside your cell phone, the iPhone, okay, that actually computes and does the whole work, okay, the whole workload is on that component, is actually this chip. This, you see, A5, they call it A5, A10, A4, A9. That's the processor for iPhone. Now, if you have an Android cell phone, then it's ARM, but I don't know how. Android ARM, okay. Yeah, okay, so ARM, like this, Cortex A15, you see? So this is the processor. Now, when the processor changes, the instruction set changes. For example, your PC, if you have a normal PC, okay, the processor that they have is not Android, but is Intel processor, okay? Looks like this, Intel, all right? In your laptops and PC or AMD. Okay, this is another processor. Now, these processors also, they have their own instruction set, okay? They're totally different. That's why a program that you write for Intel cannot be executed on an Apple cell phone, okay? You just cannot do that because the processor in Apple, in iPhone, is different than this one. Okay. Now, basically, if this processor have instructions, and we call these instructions machine instructions, and machine instructions, or machine code, okay, or machine code, and they are in binary. Like what? Like maybe there is a instruction 001 means add 01, 01. This one actually adds 1 plus 1. Okay. Then you want to add 2 plus 3. Then this is the add instruction, 2, and this is 3. Okay. You see it's binary. So now I have two instructions. This one adds 1 plus 1. This one adds 2 plus 3. Okay. But when they designed the processors, they realized that, oh my goodness, this is so difficult. We have to, put the binary number 010101. It's so difficult. But in the beginning, right, it was like this. Then they came up with what we call the assembly language. Okay, assembly. So now here you have machine language, which is in binary, machine language. Okay. Then they came up with the assembly. Now the assembly is the same thing, except instead of 0101, you give them meaningful names. For example, 001 is add. So actually, if I want to write the assembly, it becomes like add. 1, 1. You see, you actually can see 001 is add. 1, 1. Okay. The next one becomes add 2, 3. Okay. Now, when you look at this one, your brain cannot really understand what's going on. You have to put a lot of effort. But when you look at this one, you actually can see the instructions, right? And they are both the same. So the machine actually can execute this one. How? Then you give this to what we call the assembler. You write this code by, you write this code by yourself. You give it to assembler, and the assembler can generate this, and then you give this to processor. Okay. But then they realized that for very simple stuffs, okay, maybe I want a for loop, okay, for loop, a loop. Then I have to write 10, 20 instructions. And they realized that actually this construct, the loop construct, will be repeated all over the program, okay? And then we have to keep repeating this construct and keep reusing this. So why we not just come up with another language that generates those, for example, loop construct, stuff like that for us? And then they came with what we call the high-level language, like C, C++, Python, Java, Pascal, things like that, okay? And basically, what happens here, maybe Python has an interpreter, but I don't want to get into those details. But the concept here is, what I want to tell you is this. They have what we call a compiler, okay? So now instead of writing in binary or assembly, what you do is you just write code like this: for int I equals to 0, I less than 10, I plus plus. You write something like this. This is C code, okay? And then you give it to, you give this code to, you give this code to compiler, then compiler compile your code, and this is the loop, okay? And then generates a lot of machine instruction like this, and then you give it to the processor, all right? So here is better because instead of writing, for example, for loop, you have to write 20 instructions like this, 20, okay? Instead of writing 20, you just write one line, okay? It's better. And that actually continued to work until 1990s. the late 1980s and 1990s. And after that, they realized that for example, your friend said the matrix multiplication, okay? For a simple matrix multiplication, you need a loop in loop like this. So you remember, I'm not sure if you remember or not. This is the matrix, right? It has like I and J, that's the dimension. If you want to multiply, and that's I and J. So you have to pick one column, okay, and multiply. This is one row and multiply by many, many columns like this, okay? Bing, bing, bing. You remember this? And then the next row, and then you repeat this again and again and again and again. So this is like kind of loop in loop, okay? So if I want to write a C program that performs the multiplication, right? Then I have to write something like 4, and then here int j equals to 0, j is less than 10, for example, whatever, j plus plus, okay? Right? This is my loop. This thing, okay, is my loop to perform the matrix multiplication. But look, if I want to do a lot of matrix arithmetic, then I have to have a lot of code, and then we face the same problem. I have to write a lot of code. And then they say, why you just don't come up with another higher level language, which we call, for example, MATLAB. In MATLAB, you can actually, for example, if this is a 10 by 2 and 2 by 10 matrices, then I can, for example, this is A, this is B. I can just write, I define A is whatever it is, B whatever it is in MATLAB, right? And then I just say A times B. That's it. Only one line. Can you believe that? Only one line. And then what happens is that the MATLAB gets this line and generates this line, this for loop by itself, okay? You never know. And then the for loop will be translated to binary, and then the binary will be given to processor. Okay, so you don't need to actually write this loop in loop. You just write this, only one line. Okay, so that's why scientists, right? Scientists that work on, you know, let's say huge data, or they want to simulate this stuff, they just don't want to pay attention to programming aspects of their goal. What they want is just to multiply a matrix. They really don't want to spend their time writing code, okay? So they use the MATLAB. Now, they call this fourth generation programming language, okay? Fourth generation, like the fighter jet, right? Now the F-13 fighter jet, okay, they call it fifth generation, it's still small, blah, blah. Okay, F-22 is fourth generation, and so on, right? Everything is like this. Even the Android cell phone, they had first generation, second generation. iPhone 1 was the first generation, okay? Now, look at this. If this is fourth generation, now you know that actually C, C++, stuff like that, they are the third gen programming language. Assembler is the second generation, and machine code is the first gen, right? Now you understand, okay? Now, MATLAB actually is we call it fourth gen. This one, they call it high level, but this is like super high level. There is another one, fifth gen. Now in this one, you don't even write code. So you don't even write this. So you might, write some symbols, draw like drawing circuit, things like that. But it's not official, so we kind of like stuck at this point. Okay. Now this one. So next time when someone says, "What is MATLAB?" you just say it's a fourth generation programming language that helps the programmers not to write lengthy code. So the code is not lengthy. That's why scientists use it. So now with this thing in mind, right, we actually can use MATLAB because what we want is we just want to do some task like what? Like simulation. Okay. So with MATLAB, which is a programming language, plus there at the MATLAB tool, they call it toolbox. Okay. Then you can do everything you can imagine with the computer. You can do. Okay, programming, any kind of programming. Now there is a toolbox that called Simulink. Simulink. Simulation. Simulink. Okay, MATLAB. This one. Simulation link. Yeah, this one. Okay. Graphical programming environment, right? You see, that's kind of like belongs to that 5th generation. So you don't even have to write code. You just put the circuit, right? And then you simulate graphical. You just put the components and you simulate. So that's why you actually can use the MATLAB with that toolbox to generate logic circuits, okay? But this one needs a little bit of you performing some self-study. Okay, so it's difficult. Anyway, so this is actually important because I know a lot of students, they don't know this kind of perspective. So it's actually helpful, especially for this computer engineering students. Right? Now you know the system, how it works, how programming languages developed. Now, question? Question? No questions. So just pick one that can generate waveform. Now let's go to our 2 days lecture note. You can download it from AULMS, big number 1 from here. Big number 1. Okay, here. So annotate PDF, describe big number 1. Hold on, I want to get some coffee. Wait 5 minutes, okay? I'm thirsty. So hold on. Okay, I'm back. Yeah, I was thirsty. I really need coffee. The afternoon session is very hard to carry on. Okay, so, all right, so today, what happened last week? Last week you learned about simple logic gates, and then you pick a simulator on your own, and then you just observe the effect of simulating, for example, an AND gate or OR gate or some simple things, right? But this week, we are going to, so last week it was only one logic gate, maximum 2. But this week, we are going to combine these logic gates to create larger circuits. When I say large, it doesn't mean 1 million, but this is actually the key. It's a small SSI, a small scale integrated circuits, okay, small. When I say small, it means maybe 10 or 20 logic gates. And the word here, combinational, okay, comes from the root is combine, to combine, okay? So you combine logic gates and then you make combinatorial, or combinational, okay? Combinational, yeah. Circuit means a circuit that combines a bunch of logic gates, okay? So today we're gonna learn about these kinds of circuits. Now, so look, this is a NAND gate, right? What I can do is to draw a box. Can you see the blue box? Draw a box, and I say, hey, can you just ignore what is inside and pay attention to the behavior only? That's actually what you do when you write this symbol, okay, the NAND gate. Okay, there is no such thing like this in real world. Have you ever seen something like this in real world? No. So what is it? Actually, this is just a symbol that represents a bunch of transistors. So here inside you have transistors, okay, and resistors, and then maybe some capacitors, okay, like this. There are many things here, components here, okay. So these stuffs that are here, right, I just tell to the one who I want to convey the message, talk about this circuit, that I tell him, hey, you know, can you just ignore what is inside and go one step above in abstraction layer? Just try to hide the details and go one layer up, okay? And then instead of showing what is inside this, which is actually a bunch of transistors, then I show to the other engineer only a symbol like this. And I said, just pay attention to this, okay, to the behavior. All right, so I'm gonna do the same thing. I just say, hey, you know, this is the box, just pay attention to what is the input, what goes in and what comes out. Okay, so the blue box. Now, if I combine these blue boxes next to each other and come up with a more complex circuit like this, then I can actually do the same thing. I say, hey, you know, just do not pay attention to the details of what is inside and just consider this circuit as a whole, okay? And pay attention to what goes in and what comes out, okay? Now you have a paper box. And then I can actually continue and put the paper boxes next to each other, you see? All right, now here the abstraction level actually goes up, okay? So you cannot see the details of these paper boxes. There is nothing here, okay? But you know that there are a lot of things inside, okay? And then I tell you, hey, you know, you actually can combine these, build very complex circuits, but at the end, the principle is the same. You just have a box, right? A box, and then you have a bunch of inputs and a bunch of outputs. Can you see this? It's clear? So basically, the general schematic for these kinds of circuits that, you know, that is being constructed by a bunch of logic gates is this. Input, some stuff's happening here that we don't care, and then output. Of course, if I pay attention to this one, this is important. So if, for example, if the input goes here, okay, and it takes 1 second, of course, 1 second is because we are very familiar with seconds, so I just say 1 second. But these logic gates are very fast. Their speed is in unit of nanosecond, but just 1 second. So it takes 1 second from the input to go through it and appear here. So if I have 1 second, then from this point to this point, actually it takes 2 seconds, right? Now, if I have an input change here, then you see, in order for this input to propagate and reaches the output, then 1 second here, 1 second here, I actually have to wait 4 seconds, right? 4 seconds. Now, this is actually very important because now I change the input and I wait for the output. What's the most reliable timing for me to wait and get the proper output? Then the question is that I actually have to find the longest path. Now, what is the longest path here? Actually, is this one. Look, this is the longest. 1, 2, 3, 4, 5. So the signal, if it goes through this, right, it actually takes 5 seconds, right? Each box takes 1 second, right? 1, 2, 3, 4, 5. So here I say the longest path for this circuit is 5 seconds. Okay, so it means if I change something, for example, at time t equals to 0, I change something at input, then I have to wait for time 2, okay? And the duration of this is 5 seconds. To see that change, to have its impact on the output properly. So if I change this input faster, like this, faster means shorter than 5 seconds, okay? Then I cannot have a stable output. A stable output. Okay, so the output is invalid because I changed the input so fast. It just can't propagate through these boxes. Does it make sense? It goes to here, right? And then you change something, then it has to go again. So everything that is being computed is invalid because the input is changed, okay? And this, what I just explained, is called propagation delay. This is actually propagation delay. It's not related to today's experiment, but just for you just to understand, okay? That combination of circuits, they have a very important characteristics called propagation delay, all right? And that is the delay that cause your processor to consume time. So that's why computation by computers takes time, okay? If your algorithm is so complex, then you have to wait more or longer because of this delay, okay? Now, if you can come up with, I really thought about this a lot when I was in PhD program. I wanted to find my thesis title, and I kind of like, can I, come up with some mechanism that takes no time? So no propagation delay means I can compute things in 0 time. Think about it, okay? Means I can actually solve, I can access to the passwords of all websites in no time, because I can actually get the encrypted what we call it, the encrypted key, okay? And then I try, because for me the computation costs nothing, and then I try everything on it and it costs 0 time. Finally I get the answer, right? But this is actually goes against the law of physics, okay? So it's impossible. For computation you have to pay. You have to pay some time. It's the cost of computation, okay? No, this is actually, I really talk, because now is lab, right? But we are not in the class, but I really like to talk about this stuff. Look at this. Imagine a wall. This is a wall, right? And then you shoot a bullet towards this wall. So this bullet travels and it hits the wall, right? And it actually penetrates the wall like this. This is the wall, right? It goes through it and then it falls, right? When the experiment is done, then you come up with a structure like this, right? No. Think about it. How does the wall know how much to go inside or get deformed? How much? You might say, oh, because there's a force here, right? There's force. The force. But I understand it. But when the force has the impact, okay, that impact moment, right? Then there must be a calculation by the universe. Okay, this is a calculation. Should you go this much or this much, or that's the calculation. And it seems to me that this calculation is actually happening without spending any time. So the wall doesn't say, let me think how much I have to go inside because of this impact, right? The nature just happens, you know, everything in nature happens, right? It just happens without any time. Think about it, right? But if you say no, it doesn't happen, there must be a fraction of time, okay? A fraction of time for this wall to calculate how much to go inside, right? Then suddenly that theory that the people talk about comes up, that they say, oh, okay, so if everything that happens around you, actually you hit something like this, right? Then my hand must calculate how much to go inside, right? Then that actually maybe indicates that we are living in a simulation and another computer is running this world. So that computer must calculate. You see the point, my point? Does it make sense? That computer must calculate, and that's why it takes time. But anyway, and if there is no time spent on calculating the events, then there might be a way for us to calculate, to compute without spending time, because that's actually happening all the time in nature. It's happening, right? Anyway, so this is actually something you can, you know, blow your mind. Think about it until your mind gets blown. Anyway, so, but in the world that we live in, when you change the input, there is a delay, okay, for this signal to travel. We call it propagation delay, and then you get the output. That's it. That's everything, okay? Now, if I show you this circuit, right, this one, I say, hey, look at this, and tell me what does it do. You might say, oh, you know, it's a kind of circuit that if you try to explain the behavior of the circuit, right? If you put 0, 0, 0, then you will get 1, 0. If you put 1, 0, 1, you will get 1, 1. If you put 0, 0, 0, and so on, you try to explain to me what combinations of input will give what combinations of output. You're trying to explain this, okay? This is one way. You're trying to tell me what this circuit does. One way is this. Another way is that you give me the equation of that output. We call that equation a Boolean expression. Okay, this is the same thing. It says, hey, you know, engineer A telling to engineer B, Mr. B, this is actually what this circuit does. It performs a NAND, see? And you know what is a NAND, right? So in English, you just say, hey, you know, it performs a NAND operation. A NAND operation. But that's English. How are you gonna say this in mathematical form? You just say, hey, you know, it performs a NAND. B and C inverted. How did I get this? It's very easy. How did I get that? You just have to trace the function. You see, this is the output F2. You trace it back. And this is a NAND, okay? NAND from B and C. So this is B and C. So B and C, and this is this bubble inverter NAND. So I can say F2 is B and C not. So that's how I got it. That's it. So now, can you see from the schematic, I can easily get the Boolean expression, right? With your eyes, you just trace and put the logic, right? So from a schematic, you can get the Boolean expression. Now, from Boolean expression, you actually can get what we call the truth table. Truth table is the same thing. When I tell you, hey, tell me what does it do? You try to explain, hey, you know, this circuit behavior is like this. If I put 0, 0, 0, I get 1, 0. This is actually truth table. Truth table says, what happens if you put 0, 0, 0, all 0 as input? What happens to output? That's truth table, okay? Now, in order to write the truth table, you count the number of inputs. For example, in that case, it's 3. And then you write all the combinations from 0, 0, 0. You see 0, 0, 1, 0, 1, 0, all the way to 1, 1, 1. Now, you have 3 inputs, so all combinations 2 to the power of n, which is 3, 2 to the power of 3 is 8, 0 to 7, okay? And then you want to write the truth table, let's say for this equation. Now, I suggest you to come up with the smallest term. What is the smallest one? AB. So I calculate the AB, okay? I put my finger on top of A and B, and then like this, I AND them together and put the result here, okay? Now, this is not what I want. I want the AB bar. You see the bar? So, AB bar. So now because I got the AB so fast and easy, right? So what is AB bar? You just invert it. And believe me, you in the exam, right? You cannot make a mistake. You just follow my steps, right? And then you repeat the same thing for AC, and they get the AC bar. But that's not what I want. What I want AB bar and AC bar. Okay. So I write it here, AB bar and AC bar. Okay. So I put my fingers on top of this column and this column, and I AND them together, and like this. AND them together, okay, and write the answer here. Okay, and so on. You go down. But this is not what I want. What do I want really? I want another, you see, I want the inversion of that. So I got this already. And what's the inversion? You invert this, okay? Invert. So every 1 becomes 0. Every 0 becomes 1. That's it. And actually now this is the truth table of function f1, the output f1. So it just tells to another engineer what happens when all the input is 0. What happens? The output is 0. What happens when all the input is 1? What happens? Look, that's what's going to happen. The output will be 1. And so on. Okay? Now, this is a truth table. Now, if I give you this table, and I say, you know, I have a circuit that behaves like this. Can you draw that circuit? Can you draw it? The answer is yes. This is the way that you do. First, you have to know what is a minterm. Okay? Minterm. Let's say I have a circuit with 2 inputs, X and Y. Then the minterms of that circuit is defined like this. We have 4 minterms. X prime, Y prime, X prime, Y, X, Y prime, X, Y. So minterms is the combination of all inputs. But you really don't know what is X. If X is 0, Y is 0, then this minterm is what? Is 1. Why? Because 0 prime and Y prime. Oh, and 0 prime. So this becomes 1 and 1. The answer is 1. Okay? So how about this one? You can just replace 0 here and 0 here, and so on. Okay? Everything else will become 0, 0, 0. Only this will be 1. But we really don't know, and we don't care what is X. X is 0 or 1. We don't care. We just say whatever the X is, then this is X prime. Whatever the Y is, that one is Y prime. If the Y is 0, then that thing Y prime become 1. If the Y is 1, Y prime becomes 0, right? This is the meaning of minterm. You try to come up with all combinations without really knowing the value, okay? Now, minterm is a term, a series of AND signals that set the function to 1. Now, if I say find the minterms of function f1, then you look, there are 3 points, 1, 2, 3 points, right? That this function is 1. Is that correct? 3 points, okay? And then you just, with your eyes, right, track to find the row number. And then you immediately say, this is minterm number 5, minterm number 6, and minterm number 7. And what is minterm number 5? I write it here, maybe here. Look, is A, because A is 1, right? So is A, B bar, C. Can you see that? How about minterm number 6? 6 I write here. Is A, B, C bar. A, B, C bar. How about 7? 7 is A, B, C. Okay? If it was 0, it was A bar, B bar, the minterm, C bar. Okay? Now, what really we mean minterm? Okay? Minterm number 5, look at this. I'm going to rewrite it here. A, B bar, C. Okay. Now, can you tell me the values of A, B, C that will set this, be careful, this is and here. So we don't write the dots, okay? Usually we just omit it. But you have to know there is an A and B bar and C, okay? Can you tell me the values of these three signals A, B, C that set this term to 1? What values the A, B, C should have in the chat room? Come on, I'm gonna give a plus to the first student. What values should the A, B, and C have so that thing will generate a 1? A, B, bar, C. Come on, first student. No, 1, 0, 1. L dot, let me see. Yeah, correct, L dot. Okay, so L dot MR, this guy. Okay, correct. Yes, the only, pay attention, the only way for this thing to give 1 is when A is 1, B is 0, C is 1. Correct? That, look at this, that's the value. A, 0, 1. That's why we write like this. Now look, if the A becomes 0, what happens? This 0 and with anything will give you 0. So if B is 1, what happens? If B is 1, B is 1, then 1 prime make this 0, and 0 and with anything will give you 0. You see? So the only time that this thing will give you 1 is when you have this combination. When you have 1, 0, 1, it is guaranteed 100% that this thing will be 1. Correct? Correct? Guaranteed. It's a guarantee. 1, 0, 1, and you will get a 1. Okay? Now, this is actually a guarantee. If I put this A bar, B bar, C bar in the equation, then I will have a 1 generated from it. Now, if I just OR this, you see OR, with the next one, which is A, B, C bar. I OR this with the next one. Then this one guaranteed, it is guaranteed 100% to generate a 1 when A is 1, B is 1, C is 0. Right? Here. Guaranteed. Then I put next to them A, B, C. And this one is guaranteed 100% to generate a 1 when A is 1, B is 1, C is 1. Right? So when we reach to M5, this one give me a 1. When I reach to M1, this one gives you 1. When I reach to M7, this one gives me a 1. And if I OR them, right? So in any given moment, one of them will fire that 1. And if one of them become 1, the function f will be 1. That's the reason why we OR them. We say a min term is the all OR, you see, OR of all the terms that set the function to 1. You have to OR them, okay? Now it becomes crystal clear. Now, look at this. So I have M5, M6, and M7. This is the function F1, okay? Now, Why do I call this a function? This is actually the output F1, right? Look at this, look at the circuit. Output, okay? But what is in mathematics, what is a function? So if I want to show you a function, it's something like this. In math, okay, we say this is the function f, and it receives an input. You just put an input here, okay, and it does something on this input, and it spits out the output. So in, out, right? This is the function f. For example, if I give this function the value x, it will give me the value y. And then they show what happens inside this function on the input x with something like this. And they usually write this like this: f of x. So x is the input, this is the function, performs something on it, and then it outputs the y. Okay? And then later on, they actually replace this with equal sign. Okay. So I'm not sure if you remember this or not, right? So this is actually the same thing. The f1, actually, the f1 is a function that gets, you see the x, gets what? A, B, and C as the input, and then outputs, actually this is the output, right? Outputs the result. You see, it's a function. It's a function. So digital circuit, combinational circuits, right? They're functions. Now I show them with the Boolean expressions, right? Look at this. I told you with this, I can get this truth table. And with this truth table, I can get this. But why this thing is not the same as this thing? Compare. Look at this. Is it the same? It's not the same. The answer is that actually they are the same. But this thing is optimized. They are the same. You will see later. This thing is optimized. But this equation here, not optimized. Believe me, you can actually play with this, okay, with mathematics. You see, one hint, you can actually take the AB and AB, right? Take it out like this, AB, and C bar or C. What is it? C or C bar is always 1, 1. So this thing actually can be AB, right? Now, there are actually laws, okay, that you can convert this AB bar C and AB, right, to this. You can use that, okay? I don't want to get into that. It actually is the same, believe me, okay? You have to perform some arithmetic here. Now, the one that is not optimized has a name. We call it canonical expression of function f. So if it's not optimized and it has all the terms for all the min terms that set the function to 1, so how many ones we have? 1, 2, 3. How many terms we have? 1, 2, 3. So this is called canonical. Canonical. Okay. Now, one way is to write the equation like this, but we also can just simply write the min terms number. You see 5, 6, 7. Now, what is some notation is to even make this more compact. So you say the function f1, you see, with the input a, b, c equals to summation of midterms. You read it like this: midterm 5, 6, 7. Okay. Now, a lot of students don't pay attention to this. This is very important. Here, the order does matter. You cannot have something like this and expect the same behavior. So when you write like this, here the A is MSB. and the C is LSB. M, most significant. L, least significant. Now, now if I want you to understand the most and the least significant bit, I give you one example. Let's say you borrow 1,001 baht from me, and after 1 month, my salary is finished, and I come and say, come on, man, give the damn money back. I really need the money. Give it back. And you say, I don't have. Can you help me a little bit? And I say, okay, I will help you by removing one of these ones. Now, which one you want to pick? Just remove and give me the value of that money. And you agree. If you are clever, you remove this one, the right one. Because if you remove this one, how much you have to pay? Let's say this is baht. Only 1 baht. But if you remove this one, then you have to pay 1,000 baht. Right? Does it make sense? So this is just 1 baht. This is 1,000 baht. Both of them are 1. But this is the least important. Least important. This is the most important. Most important. Right? 1,000 is a lot. So the right side is the most M. Most. Now here in binary we say significant. Bit. Here we say most important digit. And here it becomes the least significant bit. So now you understand the right side is not, not important, not significant. If you remove it, it's okay, it's just 1 baht. But the left side is very important, very important. You just remove it, you lose 1,000. Okay. Now, a lot of the students, they confuse. You see, if I have CBA, right? And look at the midterm 5. You remember it was A, B bar, C. You remember? The midterm, right? So now what happens if MSB and LSB changes like this, right? The outcome is C, B bar, A. Can you see that? And what is the operands between is and. Now, are they the same? They're the same. Can you see they are the same? Only A and C switch, right? But this is a problem. For some cases like this, they are the same. But let's say for M6, right? M6 is A, B, C bar. If it's like this, okay? But if it's like this, is C, B, A bar, right? Are they the same? They are not the same. They are not. Can you see that? This is the midterm number 6. This is midterm number 5. So a lot of the students, because sometimes by accident, like as I show you here. Now because the B is here, the command, right? So even you switch the A and C, it becomes the same, right? That is the source of students confused, and they think they can actually switch this. Okay, because sometimes actually they switch and they get the right answer. But they're just lucky. Okay, they're just lucky because now you can actually switch the A and C here, no problem, right? But here you cannot switch A and C, because if you switch, here is C bar, here is A bar. Can you see that? So the answer is different. Okay, now, as I told you, you can, if I give you the schematic, you can get the Boolean expression, and if I give you the Boolean expression, you can get the truth table, and from the truth table, you can go back to canonical Boolean expression, and then you can go to the schematic and so on. So it really doesn't matter what form of circuit I give you, you can always change it, okay? Now what I'm gonna do, I don't wanna give you a break. I wanna explain this this section, okay? And the experiment, and then we close the session, okay? Then what you have to do is just go and simulate and submit the report next week. Is that okay? I think it's better. No break, okay? Now is actually, I'm supposed to give you a break now. But I think if you just bear with me a little bit and then we finish this, okay? Hello?
Yes,
Am I
sir.
on? You hear me?
Yes, sir.
Okay.
Yes.
Okay, so look at this. This is actually very important, circuit implementation. Now this is about, okay, now you learn about the logic gates and or blah, blah, right? But now I tell you, you're at home, go to your kitchen or your backyard or wherever you want to go, workshop, and build a logic gate. Can you build this one? Can you build a device that performs the AND gate? Means implement it. Can you do that? How are you gonna do that? Think about it. Go to your kitchen or go wherever you want to go. Build this. Build this one. Can you? Can you do this? Somebody say yes or no. Come on.
Yes.
Yes. How? How? Who said yes?
LDAT.
Eldad, how are you going to build? Tell me. Explain. Build one. How?
Logic gate. How to build logic gate?
What?
To
Build
build
an AND gate. How are you going to build an AND gate?
using CMOS.
Where is the CMOS? Tell me. Build a CMOS now. Where is it? Eldad.
Yes.
Where is that CMOS that you saw? Where is it? Is it under your carpet?
No,
Your
like,
kitchen? Where is it?
Some material to build like transistor. Then we're gonna build.
Yeah, transistor. You have to have a transistor. Where is that transistor? Can you build a transistor?
Yes, using silicium, germanium.
Where is the germanium? Find one, build one. Where is it?
We have to mine it.
Mine it. Where? You see. And then let's say you have the germanium mined. Okay. You have it in your kitchen. You have it in your place. Where is it? And then how you gonna connect them? How are you gonna do that? You see, my point is this. Now he actually, the elder, right, is a little bit, he knows about the logic gate, right? And he mentioned the CMOS and transistor. We actually knew about this logic gate since 19th century, 80 something, okay? We knew about this, but we could never ever build a computer, okay? Because we have not invented the transistor. So that's why, you see, the implementation is this. Implementation means you build this thing in real life. It's very important, okay? And that's why transistor is called the most important invention of mankind. Is just right now, today, at this moment, okay? Now you are truly, I'm trying you to truly understand this, that the mankind, the humans, me and you and all the mankinds on this planet, right? They knew about logic gates but they could never implement it. They could never build this thing in real life. They could not. Until they invented transistor, okay? Now, I always talk about the seesaw and the inverter. So a lot of people, they say, you know, actually the history of computer comes from what we call the Babbage machine. It's actually mechanical. Let me show you. Babbage, something like this, Babbage machine. Charles Babbage, yeah. Yeah, you see? Look at it. This is the first computer. Can you see that? This is actually pure mechanical parts, right? Moving. Can you see that? So this is the time that they did not have transistor. So they had to, you know, come up with some parts that move, right? So for the inverter, think about it. You can actually come up with a seesaw, right? If this is low, this goes high, right? When this is high, this goes low. Is that an inverter? Yes. Yes. Okay. But there are two problems. First is that this is a slow, like you have to put your hand here and pull. Okay. So maybe 500 millisecond takes time for this pull, and it uses a lot of energy, your muscle, right? And then you push this. Okay. Another problem is that how you gonna build circuits means now you have one inverter, two inverter. How about two inverter? The answer is that, oh, actually you can. So you just connect this one to the second one, right? So if this is low, this is high, and this become low again, right? Similar to this. But the problem is this. How are you gonna build AND? Build the AND gate, which is this one, using that component. And you get stuck here, you cannot. You cannot. So basically, there is no mechanical way that can give you the AND gate. There is none, okay? So that's why we are stuck. We couldn't build one. Now, until actually before transistors, we invented what we call the vacuum tube, okay? Which is something like this, okay? Vacuum tube. No logic, maybe. Yeah, you see, now they could actually put the vacuum tubes next to each other, and these are actually the resistors. Can you see the resistors? All right, and these are like two vacuum tube, two to make an inverter and like that. Okay, let me see if I can find a better. Yeah, you see, yeah, that's actually a vacuum tube digital circuit. Can you see that? Now there are two problems with this. First, the vacuum tube, the required voltage is high. Second, there is a vacuum tube. There is a heating element that needs, you see, is glowing. Let me maybe go to, oh, I saw. Here. You see? Okay. Where is it? Where is that schematic? Here, you see? So there is, you see the heater, can you see this element? Curly, like a spring, right? So in order for this thing to function, you have to apply the voltage, and then you wait for like 30 seconds until this becomes hot, and then this thing works, okay? And then if you pay attention, vacuum means there should not be any air inside, no air, okay? So there is this glassy thing, so it's actually susceptible to shake and it breaks. So, and there is another thing is the lifespan. How much is the lifespan? 6 months, you see? It means you build something like a computer, and after 6 months, the transistor, which is actually built from vacuum tube, right? It fails. You have to replace them. You have to maintain it. 6 months is just the average. Sometimes after 2 months, they burn. The heating element inside burns. You have to replace it, okay? So that's why they could not implement, this is very important, okay? Implement the logic gate until they build one. Build the transistor. They invented the transistor in 1947. Now let's look at the transistor that your friend says, okay? Transistor. Maybe first transistor. Yeah, that's it. This is the first, yeah. This is the picture of the first transistor, this one. Look at it, it's actually huge. Can you see that? See? So it has, I don't know how to open it. Okay, anyway. So it has 3 pins. Can you see 3 pins? And this, the germanium that your friend said, you have to mine it and bring it and then melt it, and then you have to add purity, a lot of things, right? But the thing is that, can you make it? To your surprise, actually, not many countries can produce this, okay? So this is very important because we can gain a lot of knowledge and learn, come to university and learn a lot of stuff, but when it comes to this phase, the implementation phase, okay, that can you really make one, then a lot of people fail. A lot of people fail. So implementation, now I hope that you understood, right? What's the meaning of implementation? When I say logic implementation, means you know the theory, now it's time to bring it into life. Build one, and that's called implementation, okay? And the problem is that not every country actually can build these things. Yeah, and that actually differentiates nations. Now, a lot of people all over the world, they know about nuclear reaction. You just take a physics 1 or physics 2 course, advanced physics 1 or 2, then they teach you, right? But how many can build a nuclear bomb? And you see, that's actually make a difference, because look at that's the implementation of the nuclear science, right? So look at the United Nations, UN. How many permanent members do we have? Means the ones that with the most power. That's actually very interesting thing about the implementation related to this. How many we have? Transistor. Yeah, transistor. We have 5, right? 5. One of them is France. France population. Look at this. 67 million population is a permanent member in United Nations Security Council. Now, look at India. 1.3 billion is not a permanent member. Look at China is, okay, China is. Look at Japan. 126 million. Almost double of French population, but they're not. Why? Anyone here knowing why? Why is that? Hello? Thinking? Oh, your friend actually could make this one. Your friend, yeah, that's what I want. Your friend actually, yeah. So you can actually use the circuit. What is this? Every circuit? Yeah, you can actually use this one. So why? Why? Nuclear bomb. You really don't know? None of you can know? Because these countries, they have nuclear bomb. They have the bomb. But Japan does not have the bomb. So even they are bigger, maybe even more powerful. But because when it comes to implementation of this nuclear knowledge, right, they could not, or they were not allowed. You see the implementation, how important it is. So for my PhD, right, I could go for AI. This is actually very important. Or, some neural network stuffs, very, fancy words. But I looked, okay, I thought about it. And I realized if you want to go for PhD in AI, then you want to run AI on what? On a computer, on a PC, right? You have to have a PC to run this AI on, right? I don't know how to build this. I don't know how to implement this PC. Then why should I learn the AI? Because if I learn the AI and nobody gives me a PC, then I cannot just run those advanced algorithms because I don't have the PC. I don't have the processor. So I have to actually, before get to AI, I have to know how to build the transistor, how to build the processor, how to build a PC, how to build an operating system. Then I can get to AI. But when I don't know this implementation of the PC, studying this is actually nonsense. You have to, imagine, about AI, but you can not have a PC. Similar to this one, about the NAND gate, but they will not give you the silicon. You cannot get the silicon. That's actually what happened to Huawei. They didn't give the Huawei the processor. So think about it, really. They didn't give the PC. So how are you going to run the AI? You cannot run. Now a lot of people say, oh, it's impossible. They will give you. No, they don't. Now look at what happened. Now you just search for Iran. Look at this. US seizure of Iran linked websites, short-sighted analysis. But what happened? Can you believe the America when they say free word, the word of democracy, free speech, right? Can you believe, because the internet, actually the domains on the website controlled by America, they seized the Iranian, state-run Iranian websites. Can you believe that? 36 websites, can you see that? So don't think that the Google is for you and they will never stop you. There will be one day that they say, sorry, you cannot use Google. Think about that. If they tell you cannot use Google, think about that. That's why China and Russia, Google, the China search engine, the Chinese, it's called Baidu. They have a search engine. The Russian one, Yandex, they are similar to Google. Why is that? Because they realize that the same thing. Now, right now, the Chinese actually, so the website is press TV, you see .com. You cannot open it. America, the land of free speech and democracy, they close this. Think about that. So much democracy that they shut down the free speech. If you want to understand what is press TV, okay, this is the similar website like RT News. This is run by Russians, RT, or like CCTV, run by CCTV by Chinese. No, CCTV News. Right? Imagine they shut down this. Okay. Now, back to this. This is actually the most important if you want to really contribute to your country and make your country to be independent. These things that we went through is not important. This is the important part. The implementation means, okay, now I learn about the gates. How am I going to build one? Very important. Okay, so all right. So now I keep emphasizing on this because really nowadays is, you know, a lot of people hold a lot of degree, but they cannot build the thing, right? And this academic degrees is fading out. Now what is important is practical skills. Can you build this or not? Now your friend says the CMOS and the mining of germanium and silicon and stuff. Yeah, but can you really do that? Can you really go and find? And it's very difficult. Believe me, it's difficult. You know, you have to actually, when you mine, what is mining? You just break the stones, right? And you have a rock, right? How are you gonna make this? Because the silicon is inside this rock, mixed with dirt. How are you gonna extract the silicon and bring it to 99% purity? Oh my God. You can actually, these things are done long time ago, but you go and you study how many processes have to be performed on this. There's a lot of processes, a lot of steps, difficult ones. Anyway, so before, yeah, question.
Is there like in the gate there are they define like like limited components inside?
Limited? What?
No, I mean like as we have the gates or like lands, like all gates, and we can have like a specific component inside, or it depends on each gate, like transistor, and we have like
what you're talking about? What you're talking about the gates? Logic gate?
I'm talking about. I would like to ask about the component which is inside.
Okay, this actually you will learn it in digital logic design course. Okay, so AND gates. Okay, AND gates. Let's say BJT technology. Okay, so basically for now, what you should know is that the logic gates can be implemented or constructed when we could come up with transistor. Okay, now we have different kinds of transistor. We have BJT transistor, we have field effect transistor. The one that your friend said CMOS is actually a field effect. Okay, so if you want to use the AND gate using, so you should know that if you have transistor, okay, you can build logic gates. That's it. Now we have different, many actually ways to build transistors. For example, one is bipolar junction transistor, and if you have two of them, look at this. Two transistor, you can buy it. Okay, you can buy the 2N222. So let me show you. So 2N222 transistor, you can buy this. I don't know how much is it, but it's not expensive. So it looks like this, okay? Look like this, okay? You can buy this. Now, if you have two, you see that it has 3 pins, 1, 2, 3 pins, okay? If you two transistor, and then you need 1, 2, 3 resistor, okay? And there is this diode too, 1 diode too, okay? And then you see the 5 volt here. This is actually a BJT AND gate. So for constructing an AND gate, you need 1, 2, 3, 4, 5, 6 components, okay? Does that answer your question? You can actually build this, and this is an AND gate. You can use the circuits, what's that? What's the name of the circuit, the program? This one. What is this called? Circuit what? Circuit lab or something? Every circuit. You can actually use every circuit, okay, to construct this. And then you can see, when you put 0 here, 0 here, you will get, where is the output? I think the output is here, between these transistors. You will get 0. Then you get 1 and 1, you get 1. No, the output is after R3. R3 point is the output, if I'm not mistaken. You can actually read it, okay? Go to here. is the output is here. The output is at this point. Prop this point is the output of the AND gate. Okay. Yeah, here. This is the AND gate. Now this is BJT, right? So, but you can use other FET. Now this is field effect transistor, but yeah, maybe this. Yeah, this is kind of similar, okay? So you can get a lot of, yeah, something like this. You actually can search. No, I don't know. Yeah, maybe this. Yeah. So you can, what is this? This is a NAND gate. So you need 4 FET transistors, okay? Now, the CMOS that your friend says is about the IC, okay? So, yeah. So you can, this is the same thing, but the process is different. To build this is still a transistor, okay? But the way that they make it is like a cake, okay? CMOS layers. So, can you see? It's like a cake. And you have the layer. So this is actually the IC. This is the cross section. Now you have layers on top of each other. Okay, metal, metal, metal. All right. Oh, here better one. You see? And they actually build the transistor in this way by just stacking the layers on top of each other, and they make the transistor. But the transistor, this is actually field effect, because this is the effect of the field on top. You know, the layers, when you apply electricity, they produce field, right? And then they interact, and there are a lot of actually cool. Ooh, look at this one. Yeah, this is actually, maybe this is, wow, this is very cool. What is this? So now we talk about the 3D ICs, okay? So yeah, this is the simple one. Can you see that? This is the, how many layers? You have a substrate. It holds everything, the yellow one, right? And then this is the NMOS and PMOS, okay? So when you put them together, it becomes complementary. This is actually not related to our course, don't worry. But this is the basic one. It has only 1, 2, 3 layers. Can you see? 1, 2, 3. But now look at this one. We have, wow. Maybe, yeah, this is the real one actually, you see? Wow, they can actually make a lot of crazy stuff. Right? This is not a nanometer, micrometer. So CMOS, maybe 3D IC. Yeah, now you see this is like kind of like advanced already. Many, many layers, and they connect the transistor together like this. Can you see that? Wow. Yeah, it's like this. Now this is kind of like 3D already. 3D IC, they put the transistor on top of each other. But for you, so that's actually advanced implementation, right? For this course, what you need to know is this, that in order to implement, you just need implementation, you just need transistor. And then the one that we have in our lab, the TTL, right, actually uses BJT transistor. The CMOS that your friend says uses, oh, field effect transistor, FET. Okay, question?
No, Ajahn.
Okay. This is actually cool, right? Very cool. So you kind of learn something, and then you try to put it into practice. Otherwise, I think everything becomes meaningless. Anyway, we have 2 experiments. I briefly explain to them, and then we close the session. Okay. The first one, what we want, we have a factory, and we want this factory to ensure 24 hours per 7 days availability. Means this factory should never ever shut down. So in order to achieve that, we, instead of having only 1 power generator, we have 3, P0, P1, P2. And they operate. We only need this P0, okay? But these are backup. Now, If everything working, all three working, no alarm. You don't set the alarm. But if one of them fails, you still don't set the alarm. But if the second one fails, right? Now you have only one and there is no redundancy. There is no backup anymore. So you have to raise the alarm, okay? So now you kind of know the situation. If one or two or less zero fails, no alarm. But if two, except to two or more than two fails, then you alarm, okay? So basically you have to come up with a circuit. These are some hints here, okay? First understand the problem, then recognize how many input we have? 3, right? Input from, this is actually what happens really in real life, is that you put a sensor here, there's another sensor here, another sensor here, and somehow this sensor knows how to detect if the power generator working or not, okay? Maybe by, if for example, there is an engine, maybe the engine shakes, okay? And then the sensor sense the shake. Or maybe the engine actually, the output is 500 volts or kilowatt, it really doesn't matter, okay? And then this sensor senses the voltage, not the mechanical shake, but the voltage. It senses the voltage, whatever, okay? So maybe you can, for example, sense the temperature. If the power generator working, the temperature is 100 Celsius. If it's not working, it's 20, something like that, it really doesn't matter. So the sensor sense the environment and then sends the output. 0 means not working, 1 means working. Believe me, it's like this, okay? It's like this. You have a sensor and the sensor sends a digital signal. How many you have? 3. So you actually have 3 sensors, so the input here 3. So then you have to draw the truth table. So P0, P1, P2, these are your input, okay? And this is your truth table. And then you have the alarm is the output function alarm, okay? So if 0, 0, 0 means all of them fail, then you alarm, okay? And all the way, if 1, 1, 1 means all of them working, you don't raise the alarm. Alarm is 0, okay? So after you get this alarm function here, okay, there are 8 numbers, 1, 0, whatever, okay? After you get it, you just write the canonical Boolean expression, the canonical, okay? It means you just look for what point the function is 1, and then you write the mean term, associated mean term, okay? After you do that, you draw the circuit. Oh, not by hand, okay? This is actually for before the COVID. You put it into your simulator, okay? And then now you don't implement it with TTL IC because now we are not in the lab. What you do instead is you simulate using what your friend showed. This is actually correct. Using this, something similar to this. And now what you have to give me in your report is 4 signals, 3 input, 1 output. So I can see that when the generator 1, 2 fails, when the third one works, then you actually have to raise the alarm. Means the output is 1 to alarm, right? To send a buzz like this to the environment outside. So some mechanic people, come and fix the problem. So this is the first one. Do you have any question regarding the first experiment? You do it by yourself, okay? You don't need to do it now. I want to close the session. The second one is exactly the same thing, but this is different thing. Now here, you have a missile launch, okay? There are 3 sources, Prime Minister, Defense Minister, and the operator, the launch site, okay, 3. So 3 input. If all of them say fire, then you fire. If one of them say no permission, then you don't fire the missile, okay? So here, how many input? 3 input. How many output? 1 output. Draw the truth table and write the Boolean expression, put it into simulation, run the simulation. So basically, when one of the input is 0, you don't fire, okay? It's actually very simple. but I want you to understand the process. And then you have some questions here. Yeah, this one is actually a little bit difficult, okay? You have to implement the Boolean expression using and or not, but this is a good practice. That's it. Do you have any questions? Questions? No questions?
No.
No,
Okay. Yeah, okay. I wish you good luck. Enjoy your Friday and see you next week. And you always can ask, if you get stuck, right? You can ask in Microsoft Teams. Okay? Here. Where is it? Here. Oh. Here, okay? Ask your questions here later on. All right? So we will have this kind of things for the next 2 weeks, I think. And after that, I will pick a simulator by myself, the professional one, and then all of you have to switch to that one. Okay? See you. Bye bye.
Sir, don't forget to check your email.
Natasha, no.
Yeah, I have sent the evidence of vaccination last week.
Email? You email to me? Email what?
Yeah, I sent you an email. Yesterday I actually saw your email, and that's my, and I
You
saw
send
my
me email about what?
Sinovac.
You send your homework to my email, right?
Oh no, because last week I was absent, right? And I actually
okay. Don't worry.
request you to absent. Yeah.
Okay, so let me see.
John, today I joined a bit late.
Who was late? Who was late? Oh, Kongsu.
Yes.
Okay, late. How about Ko-Rabbit? If you were absent, I will check the email. Okay. I told you that you sent me. I thought that you sent me the homework. That's why I ignored. Don't send me the homeworks, okay, in email. Okay. This guy is late. Okay, I'll check the email. Don't worry. Okay. Good luck. Bye-bye.
Goodbye, sir. Thank you.
Yeah. Now.